Hi, my name is Joshua Ball, and today I'm going to be talking to you about few-shot learning for the image classification of common flora. As a general overview, I'll be talking about the introduction to the project, the image classification problem, meta-learning and MAML, knowledge distillation, MAML results, transfer learning, some data processing and data augmentation we did, our transfer learning results, some advantages and disadvantages of each approach, as well as a overall conclusion. So basically, this project is all about comparing transfer learning and meta learning for the task of few-shot image classification. And we're going to basically want to classify 5 different classes of different flowers with good generalization ability with the least amount of data needed. And again, we're going to want to compare the few-shot implementations with a robust model trained on the complete flower dataset as a baseline for what we hope our solution to reach. The image classification problem is essentially trying to attempt to comprehend an entire image with the goal of classifying the image to a specific label. We want to analyze the image as a single object where no localization is occurring. So, for example, on the left here we can see image classification with the cat and object detection on the right where we are looking for multiple objects and trying to draw a bounding box. This isn't what we want to do. We want to simply classify the centermost object of the image. Common downfall of this, however, is the enormous amount of computational power and data needed to reach state-of-the-art levels is very high. And so that's really where few-shot learning is born from. So meta-learning really is, especially in image classification, is one trying to mimic a human's ability to quickly learn and distinguish from small dataset sizes. So we want to allow one to quickly develop and adapt to test time tasks with limited data and low computational power. So in this image below, we can see some support images as well as one query image feeding into a network where we have a parent model at the top and a student model at the bottom, where we are feeding the output of the parent model through a softmax layer into the test model through some linear classifier, where we're wanting to ultimately have a classification on the student model where the complexity is significantly lower than on the parent model. So Model-Agnostic Meta Learning, or MAML for short, is basically aiming to find a general set of model parameters such that a small number of gradient steps with a small amount of training data from a new task will result in a large improvement on that task. And MAML does so well due to its given ability to rapidly learn and reuse high-quality features. So on the right here, we can see our function theta, and it's going to be taking some step, either theta 1, 2, or 3, dramatic step in the meta-learning process, basically where it's going to be just taking some gradient step and it's going to be learning and adapting. And it takes very few steps, but the steps are so large and so dramatic and so intelligent, so to speak, that they end up allowing MAML to perform really well. So this kind of breaks down that process again with the teacher and student model, but it kind of talks about a different topic called knowledge distillation. And knowledge distillation is essentially a way for us to compress a model size while not sacrificing any major performance. So it's really nice. So going into our specific meta-agnostic model parameters that we use the parameters here seen on the right, where we use 60,000 epochs. We had our images in color, so the value was 3 or RGB. We resized all of our images to 84 by 84. And we did a k-query and k-split of 15 and 1 respectively. We had a meta-learning rate of 0.001, an in-way of 5, 4 task number, and we had the learning rate update at 0.01. We had an update step of 5 and update step test of 10. And all these parameters were really largely based off of the original MAML paper. So for our results, we had actually excellent results. Initially, we were having some difficulty making this work nicely, but just through tuning the parameters to more based off of the paper, we were able to get better results. So we can see on the left here, this is kind of our output from training. We can see how many gradient steps we were taking on the left there, where it says step and then a value. So we ended up stopping at 990 gradient steps, and at that point we reached a training accuracy of 100 across the board for all the different labels. So again, that's rose, dandelion, and etc. And we actually reached a test accuracy of 100% across the board as well. So MAML performed extremely well on our small data set. We were very happy with that. So transfer learning. Transfer learning is our other approach that we worked out here. And transfer learning essentially is where you take a generic data set on a large generic network. In our case, we used MobileNet v2. And that generic network is trained for a long time on very high performing GPUs. So for example, like MobileNet v2 was trained at Facebook, where they had a whole bunch of GPUs and a whole bunch of processing power, and they were able to make a great network based off of ImageNet to do that image classification task. And what we do is we essentially take A prime out of A, where A would be MobileNet v2, and we put that on top of our trainable network, and we want to feed in our image data set. So in our case, it's just a Flora data set, and we want to feed that in through the pre-trained layers in through the trainable layers to do our specific task of Flora classification. So this allows us to reach state-of-the-art performance without state-of-the-art time and resources. And we again want to add those MobileNet v2 layers on top of our linear sequential model. And we added a few layers after that. So we added a 2D global pooling layer to reduce our dimensionality of the output from all of those upper layers of MobileNet v2. And we also tuned our dropout L2 regularization, our ridge regression, our optimizers, and our optimizer learning rate just to help fight overtraining and help our model converge. We also utilized several different technologies such as early stopping, checkpoints, learning rate reduction on plateaus as well. So I just want to talk about knowledge distillation versus transfer learning, because they might seem fairly similar on the surface, but they're actually quite different. So knowledge distillation has a teacher model and a student model, where the student model is trained to match the softened output of the teacher model. The teacher model is a pre-trained network, and therefore backpropagation only occurs in the student model. Where transfer learning transfers the model weights from the original model, meaning that all the complexity of that original model remains the same, and as we saw in our example, we actually add more layers to the bottom of that transfer learning model, so it gets more complex. So for our data processing for our transfer learning, we did, and for MAML as well, we had 5 different classes of images separated into a subset and a complete set. So the complete set was utilized for baseline numbers, and our subset was actually used for our real experimentation. And our data split was 75, 20, and 5. And down here we can see our 5 different classes. We have a random image from each class. So we have, from left to right, roses, dandelions, daisies, sunflowers, and tulips as well. So for data processing, we decided to keep the images in color. We didn't want to remove the possibility of removing a feature that the model might end up finding useful. So we decided to keep color. And for our transfer learning models, we kept the images at 224 by 224 pixels. And on the bottom right, we can see a histogram of the rose image above, which kind of just shows the different colors of each channel and the distribution of those colors. So for our transfer learning models, we also implemented data augmentation, which artificially increases our data by 10 times at training runtime, which is really nice because you really can never have too much data regardless of how many images you have. So our complete set has a little over 4,000 images, and obviously our subset has only 25 images in the training set. So data augmentation is a really nice technology. An interesting thing though with data augmentation is you actually don't use those original images, you only use the augmented images. And those images are generated on demand at training, so they're never sitting on disk or anything like that, only in memory, and then they go away when they're no longer needed. So some of the parameters that we used for data augmentation was a rescale factor of 1 to 255. We allowed the image to have a rotation range of 40 degrees, and we allowed it to be shifted on the x and y axis by a factor of 0.2. And we allowed it to be sheared and zoomed in also by a factor of 0.2. And we also allowed a horizontal flip to occur, and we wanted the fill mode to be nearest, so that way it would be kind of zoomed in the most and kind of avoid the distortion that you get with image augmentation. So our transfer learning results with the complete set were quite good. We ended up having a 94% accuracy on the validation set. And so this transfer learning model that was trained on the complete set is really utilized for our baseline numbers to compare against the other two models. So our other two models being the MAML implementation that we saw earlier, and the transfer learning model you'll see in a bit, which is trained on the subset. So on our right here, we can see the confusion matrix of our transfer learning model trained on the complete set. And we can see that it performed quite well overall. We can see there was some confusion with the rose and tulip in both cases of rose and tulip. So we're getting some false positives on both of those ways. So this might end up being an issue with our other transfer learning model, which is trained on the subset. And you'll actually find out that it is. Those two classes and those two situations are quite exacerbated in the other implementation. So here we can see some statistics and some more detailed performance of our model. So we can see the precision and recall of our different classes for our complete set transfer learning model. And the recall is basically the sensitivity to that label. And we can see across the board, both of them are quite good, both in the 90th percentile almost across the board, except for Daisy and Rose, as we saw earlier. And our F1 scores are also very good, almost in the 90th percentile across the board. And they have a accuracy and weighted average accuracy of 90%. So overall, pretty happy with this performance. Perhaps we could have gotten it better, but with my computational ability, I think that this is a good value, good performance value. So for the transfer learning model with the limited data set, you can see that there's quite a bit more color here on the right in our confusion matrix, and that's because we ended up only getting an accuracy of 61% on the test set with this one. So we had a very high confusion on quite a few things where we're getting a lot of false positives and false negatives in nearly every class. However, Daisy and Rose and Tulip are by far our worst performing ones. So we can see that Daisy is being falsely read as sunflower, sunflowers are being read as daisies, and tulips and roses are also being confused quite a bit here. Dandelions, not so much compared to the others because they do look quite different naturally, but you can also see that there is still a bit of confusion in there. And looking at some more detailed statistics here, we can indeed confirm that Daisy and Rose are the worst performers here. So Daisy a little bit more surprising. We were expecting Rose and Tulip to be our most confused ones, but Daisy coming in there to be the worst performer, especially in recall, where it's only having a 36% recall sensitivity, which is pretty poor. Overall, we're looking at a accuracy and weighted average accuracy of 61% on the complete set. Overall, I think this is okay. Not too happy with this. We did a lot of different implementations, a lot of different hyperparameter tuning. We had to bring the learning rate pretty high on this for it to even mildly converge. So some kind of basic information about standard image classification is, you need a large amount of data splits and a large amount of data in those splits to really get a good performing model. And that model is oftentimes going to take a long time and be very computationally intensive to reach state-of-the-art levels. And it's going to very likely require many iterations and hyperparameter tuning, to get some decent performance, like ours took. Ours took several iterations of both convolutional neural networks for the transfer learning models. Both of those went through 7 to 10 different implementations to find a decent performer, which took very long. For a few shot though, kind of the general guidelines, we have a training set size of maybe 5 with 3 query images each. In our case, we decided to do 25 for the training set just because we were having some issues again with convergence, and I think that's really just perhaps the data that we got off of Kaggle that didn't perform as well as we had hoped. The advantages of few shot though really show in this experimentation and in this paper, because they allow for the rapid testing and allow for us to tune our hyperparameters very fast with lower system resources needed. And this allows for the quick acquisition of task-dependent knowledge and slow extraction of transferable knowledge. And the training time and resources needed are still low, like traditional few-shot classification seen in the MAML paper, which is the implementation that we utilized for our few-shot. So some additional disadvantages. The accuracy is still perhaps lower for large data sets compared to traditional heavy data sets for image classification. So you can see in the MAML paper that although MAML does really well in data sets that don't have a lot of very different features, like a handwriting data set, it will do very well in. But if you throw ImageNet at it, it does very poorly. It does something like 40% accuracy, 40 to 45% accuracy, but in the handwriting data set, you can expect something like 99% accuracy. So it does very well in those low feature environments, but once you have a lot of different features that have a very high variance, it struggles. And that's because, and that really goes down to why I think it's not really feasible in high-risk deployments where accuracy is more important than training time. Again, when you're talking about a very large data set with a very high variance. And transfer learning, even per the authors, is better at getting more robust models for our solution. And again, that's only for those large data sets. Because as we saw in our experimentation, and which is laid out very well in our paper, the traditional transfer learning model was trained on a complete data set and netted a very robust model with a high recall and precision ability, which was ideal for most situations. However, our transfer learning model trained on the limited data set wasn't able to generalize as well. And ultimately, we believe that was due to the data sparsity in that limited data set. But our MAML model, however, performed much better than we expected on the limited data set, achieving 100% accuracy on the training test sets as we saw earlier. So ultimately, MAML did very well. It trained very fast, and it really crushed our transfer learning model on the limited data set. And when you really think about it, it reached 100% accuracy on our limited data set, where our big, large transfer learning model that we trained in the complete data set ended up reaching 94% accuracy. And that 94% accuracy took a lot longer, a lot more tuning, a lot more data, and a lot more computational power needed. So MAML really is very impressive. You can access all the code for all 3 different implementations at my GitHub link here provided. This is also in the paper. So in summary, we talked about all these different things, such as the MAML, our MAML implementation, the different parts of MAML, transfer learning, our data processing and augmentation, our results from transfer learning, and the advantages and disadvantages of each implementation, as well as our overall conclusion and how impressive MAML ended up performing. Here's my references, and this concludes my presentation. Thank you.